Oops, it's unstable. Okay, this is the point. Nami Svaiter. Okay. Estranho. Marcar.
Okay, let's start again. So we will hear Nami Svaiter talking about Euclidean scalar field with quench additive anisotropic disorder.
Good morning. First of all, I would like to acknowledge Giorgio and Gabriel for the invitation of being here. And this is an old seminar, and this seminar is totally different because I will talk about the Euclidean version of quantum field theory. First, I would like to remember some papers that we did that we go in this direction for analog models in quantum gravity, first with light-cone fluctuations and next with wormholes physics. In '96, myself and Ford, we discussed a bath of gravitons in a curved space-time, and we showed that the effect of squeezy gravitons in the curved space-times is to put the light cone to fluctuate. Then we have light cone fluctuation if we have a bath of graviton. Instead to have a fixed light cone, we have these light cone fluctuations. And we did also 2 papers about this. And since we have this light cone fluctuation and using the Unruh ideas of analog models, with Gabriel and Gaston, we construct an analog model in random fluids of these light cone fluctuations. But instead to have light cone fluctuations, we have sound cone fluctuations. Okay. And also in quantum optics, you can have these analog models and so on. Okay, and at that time, I started to study disorder and noise in statistical field theory and in quantum field theory. And if you have statistical field theory, appears something that we call it's quencher disorder, and you have to do an average of the disorder over the free energy of the system. And people, they use the replica trick. I will talk about this later. But instead to use the replica trick, a few years ago, we found a different way to perform this average, generalizing the zeta function for a general measure. I will talk about this. Okay, and after this, we did a lot of paper using this technique. It's only a technique to perform an average of the Gibbs free energy, but we don't have the same problems that you have in the replica trick. I will talk about this. Okay. Then general relativity. We have a pseudo-Riemannian manifold. We have a local theory. Okay. And we have dynamics equations of motions. And if you go to Minkowski space-time, quantum field theory was formulated in Minkowski space-time. You have the Poincaré group, Lorentz transformation, translations, and in the operatorial approach to quantum field theory, quantum fields are not only operators, but they are operator value distributions, because you must mirror it with smooth compact support test function. This is the idea that appears in Bohr-Rosenfeld paper. You do measurement only in a region of space-time, okay? And these mirrored fields are unbounded operators in the Hilbert space. Okay. What we have? From quantum mechanics, we have the probabilistic interpretation of expectation values. And since we have a local field theory, we can construct the commutator between two mirrored fields in a space-like surface. Okay, that's it. Well done. This is the constructive program of field theory made by Whiteman and collaborators. Okay, if you try to quantize the gravitational field, we have problems about how is the causal structure and locality issues. Okay, but before quantizing gravitational field, a step before is to use the semi-classical approximation, quantum field in curved space. You have a fixed background, a classical geometry, and you have quantum fields propagating in this classical background. The black hole evaporation is a result that appears in this scenario. Okay? We can go further and discuss exactly what happens if I have a bath of gravitons. A bath of gravitons in this fixed background. And as I told you, the effect of the gravitons over the Lie cones is to put the Lie cones to fluctuate. Okay. Then, who showed that, for example, if I want to measure the Hawking effect, I cannot do astrophysical measurement. Then we can do this in the lab. For example, in Bose-Einstein condensate, this is the idea of analog models. For example, if you have, you construct a sonic black holes and you have phonons, these phonons must have a temperature, this idea to obtain the Hawking result in the laboratory. Okay. And quantum gravity effects. Can we construct quantum gravity effects, construct an analog model for quantum gravity effects? Yes, we can. For example, we can put a fluid that's a random fluid, and you have sound waves, and instead to have light cone fluctuation, we will have sound cone fluctuation. And this we call the analog model for quantum gravity effects. In this scenario of gravitons and light cone fluctuations. But quantum gravity, that it's not only, it has not only the ultraviolet problem, we have also infrared problems that's related to topology change, wormholes. Then the question is the following. it's possible to construct the same way that we construct an analog model for light cone fluctuation in the lab. It's possible to construct an analog model for topology change in condensed matter. This is the idea that I would like to discuss. Okay, I will go to the Euclidean version of quantum field theory. I did the Wick rotation, and I'm doing Euclidean quantum field theory. The advantage of this Wick rotation is that I can construct functional integrals, and I'm doing statistical field theory. There is no difference between Euclidean quantum field theory and statistical field theory. Of course, the difference is that, for example, in statistical field theory, I'm interested in thermal fluctuation. And Euclidean quantum field theory, we have quantum fluctuation. But the methods, the functional integral, we have the same math, the same background to discuss both theories, statistical field theory or Euclidean quantum field theory. Okay, then in statistical mechanics, we have the Liouville measure, we have partition function, and construct Gibbs measure. Né? You have the Hamiltonian and the temperature 1 over T, and that's it to find any observable in statistical field theory. The idea is that I can find any object that I want using the Gibbs measure. If I go to a system with infinite degrees of freedom, this measure is only formal, but I can continue to work with this framework. Then we are doing now Euclidean functional methods, okay? With some measure that's equivalent to the Gibbs measure for the case of infinite degrees of freedom. We continue using the probability concept, but now classical probability concepts, only classical probability concepts. Okay, what's the simplest situation of Euclidean field theory? For example, for a scalar field, in the pseudo-Riemannian manifold or in the Lorentz manifolds, we have the Whiteman function, the product of the field smeared. If I do an analytic continuation of this Whiteman endpoint function, I will obtain the Schwinger functions. These Schwinger functions are exactly the any-point correlation function of this Euclidean field theory. For example, for a Gaussian free field, I have this equation, and the endpoint correlation function associated to the scalar field is given by this expression here. This is quite similar to this Gibbs measure in statistical mechanics. Okay, then I'm working in Euclidean quantum field theory or statistical field theory. Doesn't matter for me. The only difference that I told you is the one you are doing thermal fluctuation, and another you are looking for quantum fluctuations. Then you have a measure, a functional measure. Is only formal because you don't have sigma additivity, but that's it. People, they have working with this formalism. Okay, now let's split to another point. Disorder in statistical field theory or in condensed matter. For example, we have some system that we have two spins, and these two spins, they are ferromagnetic, and other spins, they are antiferromagnetic. How to model this disordered, this amorphous material using some Hamiltonian. And this is the Edward Anderson Hamiltonian. The idea is quite simple. Instead to have a fixed J here in the Ising model, I put that the coupling between the spins are random. Now I can model exactly the situation of ferro and antiferro in a random way. People, they don't know how to solve the Edward Anderson model in the general case. There is no solution. But if you allow the spins, all the spins to be connected, then we are able to solve this model. This is the Sherrington-Kirkpatrick model. Because if these spins is connected to all the other spins, then you have infinite spins around them, around this spin. Then you are always above the critical dimension, and the mean field approximation is exact. This is exactly the solution that Sherrington and Kirkpatrick did. That it's possible to solve the Anderson model for the case of infinite connectivity between the spins, but to solve this model, you have to do the following. You have to average the random quantity, not in the partition function, but the log of the partition function. They call this quenched free energy. And we have a technical problem. How to perform this average of the log? It's not simple. For the case when we perform the average of the partition function, we call that the disorder is annealed. And it's quite simple. Nothing new happens in this case. But in the case of quencher disorder, it starts to appear interesting physics. Okay, then the main problem that people had is to do this average. Then they invented the replica trick. What's the replica trick? The replica trick is the following. I will construct replica of the systems, and I will do the following to perform this average here. I construct k replicas of the system, and I will use an identity. Log of x is x over n minus 1 divided by n when n goes to 0. Then instead to do the average of log, you are doing the average of z in n power. Then you transform the quenched problem in an annealed problem. Then you are able to perform the average, and in the end, you have to take n to 0. And there are two problems in this approach. First is that if you know points in the complex plane, you are not able to do an analytic extension. That there is no analytic extension in this situation. You must have open connected set of points to perform analytic continuation. And second is the following. After do this average, z over n, we will have a multiplet of fields, but you have put n to 0. Then what's the meaning of this? You have n fields, and your answer is in the case when n goes to 0. I don't understand this. I'm not able to understand this. But then that's the problem of the replica trick. First, there is no analytic continuation, because you know points, n is 1, 2, 3, and you have to goes, n goes to 0. And Parisi, he wrote something about the replica trick, the replica theory, okay? Then, okay, and in 2016, we found a different way to perform this average without the problems of the replica trick. And we call this the distributional zeta function method. And I will try to explain the idea of the method. Okay. Remember the Hawking's paper or Seeley's paper and something like this. If I have complex numbers, products of complex numbers, there is a way to regularize these complex numbers or real numbers, doesn't matter, defining the spectral zeta function associated to these numbers. You define a spectral zeta function. If I have the numbers, I define a complex function, and for some region in the complex plane, this series converge, it's okay, but I have to do an analytic extension, and I can show that this product here is exactly the analytic extension of the spectral zeta function in S equal to 0. If you take the log, then you have exactly the free energy of the system. This is exactly the Hawking paper, when he calculates the thermodynamic quantity of photon gas using the spectral zeta function. That's exactly I'm saying. For the case that you know the spectra, the free energy of the system is DDS of the spectral zeta function when you perform the analytic extension and make the derivative of the zeta function in S equal to 0. Actually, this idea is a silly idea. Hawking only used this definition to find the thermodynamic quantities of a photon gas. Okay. Now let's use this idea of the spectral zeta function for the case of the average that I want to perform for the case of the quenched disorder. And this is a technical, the definition of the object that we are dealing with. We have to introduce, to change the measure and introduce another no more spectral zeta function, but we call it a distributional zeta function, and will be clear that we are doing later. Okay, that's the definition of our distributional zeta function. We have a measure, you have a measure space, you have a measure, and that's it. Let's see how this works for our problem. Suppose I have a scalar field and a clean system. Okay, I'm doing Euclidean quantum field theory or statistical field theory. Doesn't matter, it's the same for me. I have an Hamiltonian, I have lambda phi 4, I have the phi 6, I put in the phi 6, and I have the Gaussian contribution for the Hamiltonian and the non-Gaussian contribution. I am RD, and this is my clean system. Again, this is a functional measure, formula-based measure given by this quantity. That's it. Okay. Now, suppose that I put now a disorder, a quenched disorder. I can put the disorder linear coupled with the scalar field, or I can put a disorder as a disorder mass. The first case, we call that is an additive disorder. This is a multiplicative disorder. That our disorder is coupled to phi square, okay? I have the probability distribution of the disorder, and if I have the covariance of the disorder, I can perform my average over to find the quenched free energy of the system with disorder. It's important to stress, we are not using the replica trick. We are using the same idea that Hawking used to find the free energy of a system that you have the spectrum for the case of a system with disorder. Okay. Then the definition of the free energy in this case is exactly this. I have log of z that depend of the disorder. I have the probability distribution of the disorder, and we have a functional measure, and I have to perform this average. This average is exactly the average that I defined before here, where I have this one. It is exactly the same thing. Okay, oops. Then I have to perform this average. The definition of the distributional zeta function is exactly something like the spectral zeta function with another measure. It's possible to show that in the moment when you calculate this distributional zeta function here, you can show that the free energy of the system is exactly the value of the distributional zeta function when S goes to 0. That this expression is exactly this expression here for the case where you have the spectrum. Okay. Then the idea is the quenched free energy of the system is given by the derivative of the distributional zeta function when S goes to 0. Okay, let us perform then, let us find a series representation of this quantity here. And if you do some calculation, you can show that the F, oh, it's not F, it's phi. Oh yeah, F, okay. Doing the derivative, okay, F. The free energy is written right now as the moments of the partition functions plus some additional terms that I can throw away because I can put A big enough that this ROA does not contribute. In the end of the story, I have the following. The quenched free energy is written as a series of the moments of the partition function. Let us calculate one of the moments of the partition function that is given by this quantity here. Instead to have only one field, now I have a multiplet of fields, and it appears effective Hamiltonian in each term of this series. For the case of the multiplicative disorder, what do we have? We have this. Instead to have one field, we have a multiplet of fields. We have the Gaussian contribution, it appears the 5, 4, 5, 6 here, and now we have some interaction between the I and the j components of my multiplet. Okay? Let's choose in the functional space a simplest way to continue the calculation. Let's suppose that phi I is equal phi j. In this case, the effective Hamilton is written as this. The Gaussian contribution is the same, and now it appears something interesting. The disorder is able to change the sign of the phi 4 term. Then, if I look of the series, I will have some critical k when we have a first order phase transition. Is exactly what is going here. For small k, I have this, and if I increase k, the disorder is able to produce such kind of profile for the potential for the field. I would like to stress that we are obtaining this result in the simplest case where we have all the fields the same moment equal. I can repeat the calculation without assume this. For example, suppose that instead to have multiplicative disorder, I have additive disorder. For example, take this, put a random magnetic field in the system. A random magnetic field in the system will be a random source. The continuous version, we call this the random field Ising model. If I have the random field Ising model and perform all the calculation, I will get this term for each moment of the partition function, that we have some interaction between the j and the I components. People, they work with the replica trick, they call this interaction between the replicas. But I would like to stress, there is no analytic continuation, and also you must understand this limit when n goes to 0. Means that you have the multiplet of fields with size 0. Okay. Again, in the functional space, choosing phi I is equal phi j, I have something like this. Then the effect of the disorder is like a temperature that can change the system from the disorder to other phase with a second order phase transition. That is the main idea of the distributional zeta function approach. Okay. And how non-local terms will appear? For example, if you are doing, instead of doing statistical field theory, we are doing Euclidean quantum field theory, the disorder happens only in this space. Then when you construct the effective Hamiltonian, will appear a non-local contribution, because you have integral 0 to beta, d tau, dt prime, and since the disorder is not on time, at low temperature will appear this non-local contribution. That's the problem of quantum phase transition with disorder, that you have non-local physics. Okay, with this idea, I can construct an analog model for topology change. Okay, that's some articles that we did about this. And now let's go to Euclidean quantum gravity. Euclidean quantum gravity, I have Euclidean quantum gravity. We construct this method of distributional zeta function, and now I will use this method to understand topology change. Okay, suppose a Riemannian manifold. I have matter fields, I have the gravitational field, I have the action of the matter field, the gravitational field. I have in the matter sector, I have a Gaussian contribution, I have the non-Gaussian contribution, and in the gravitational sector, I have the Einstein-Hilbert plus other terms that you have to put to make sense the theory. Okay, and what's the meaning of topology change? Topology change is the following. The effect of wormholes in the partition function is that will appear such kind of terms that connect different points. This is a non-local contribution to the partition function of the matter and gravitational field. Let's use the distributional zeta function to obtain exactly this contribution in some system with disorder. As I told you, Euclidean quantum field theory at low temperature, or if I put a statistical field theory with anisotropic disorder, I will obtain exactly this kind of contribution. That's the idea. Okay, then I have my scalar field. I have a J, that's the source, and I have a disorder field. That I know the covariance of the disorder. This F minus 1 is missing here. Okay, performing the average over the disorder using the distributional zeta function method, I have the Gaussian contribution, I have others phi4, and I have exactly some non-local contribution that's exactly as this situation here. In other words, if I have a system in statistical field theory with anisotropic disorder, I'm able to construct an effective model that has exactly the same mathematics as the Euclidean wormholes in Euclidean quantum field theory. Okay, since the disorder is an additive disorder, instead to choose that all the fields are the same in the same multiplet, I can open this and I have different fields in the same multiplet. In the end, what we have is the following. We can split the action in two contributions. One contribution, I have k-1 fields, all the fields with mass, but without disorder. And one of the components of the multiplet, now I have a disorder field. Then I have something like this. One of the components of the fields, I have the contribution of the disorder. Then that's the idea, to construct an analog model for topology change using condensed matter with anisotropic quenched disorder. Okay, how to interpret the series? You can interpret the series putting we have interaction we have something like this, and we have terms that connect different uh, terms of the series, but this is only interpretation. Okay, that the idea of the paper, the paper that we did. If we have disordered fields, we have to do the average of the log of z, the Gibbs free energy, and instead to use the replica method, we introduce a different way to perform this average, copying the spectral zeta function, changing the measure. Doing this, we are able to write the free energy as a series of the moments of the partition function. We are not doing this limit n goes to 0. It's totally different. We have this series, and with this series, we are able to discuss in the functional space if I have all the fields, the same field in each moment of the partition function or not. If we don't assume that the fields are the same, we are able to write each of the term of the series as one of the fields. They carry the disorder, and the other k-1 fields are fields without disorder. This is the idea of of our paper. That 15 years ago, we construct an analog model for Lycon fluctuation. And right now, still using disorder, we are constructing an analog model of topology change or wormhole, Euclidean wormholes in a condensed matter system with disorder. Using this method that we introduced in 2016.
Questions?
So I think in your last slide, yeah, you mentioned fluctuations of the light cone. How do you see that from any of this discussion?
No, you don't see. It's a paper that I did in 97, 98. I put this only to say that if you have Lycon fluctuation, it's possible to construct an analog model of this in random fluids. That's it. And 15 years later, we construct an analog model of wormholes, of topology change using disorder. But this does not appear in this paper. It's only the idea of construct analog models in different situations. One, Lycon fluctuation. If you have acoustic perturbation in a fluid and you have sound cones, if you put some randomness in the velocity of the wave, then you have sound cone fluctuation. This is an analog model for Lycon fluctuation. Now I'm talking about totally different. I would like to construct an analog model that have exactly this structure. Oops, no. This structure here. The partition function of matter fields and gravitational field with wormholes, Euclidean wormholes, they have this contribution. The idea is to show that in condensed matter, you are able to present exactly some model with this kind of contribution using disordered fields. Nothing to do with Lycon fluctuations.
So what kind of difficulties arise if you try to extend the distributional zeta function methods to a Lorentzian context?
Look, you have functional methods, okay? I don't understand functional methods in Lorentzian manifolds. This is meaningless. You are not able to define functional integrals in Lorentzian manifolds. That's the problem. The problem is about how to define measures. Because of the I. You have the I, and you're not able to define measure. You're unable to have this mathematics for Lorentzian manifolds. That's the problem is it's much better before.
Is there any analog to the kind of, to Wick rotation after you do this? Could you?
No, I did the Wick rotation.
Going back.
You can go back because you have the reconstruction theorem that you, from the Whiteman function, you can obtain the Schwinger function, and you can go one direction in another direction. Schroeder reconstruction theorem. We are able to, from the Schwinger function, obtain the Whiteman functions for the case of the scalar fields. Pardon?
It's not so easy to do it in this case.
It is. You have scalar fields. Of course. Yes, of course. If I don't have ultrastatic space-time, there is no. But the question that he asked was different.
But yeah, I'm just curious to start. I mean, yeah, I have no hope with if you have the quantized metric in the game. But if you're just talking about the,
I'm talking about the contribution of wormholes, that you have this kind of contribution, and I found a model in condensed matter that you have exactly this contribution. It's quite difficult to do this using the replica trick, because the replica trick, you must have the multiplet of field with zero size. I don't understand what is this. I don't understand replica trick. I really don't understand. For me, it's totally out of mathematics.
Okay, let's thank the speaker again.